A lot of people have asked me, why do you stay in Scotland? And my answer is always the same. Living in the Central Belt, I have access to our two biggest cities, and 20 minutes away, there is complete wilderness, highlands, and nature. I have only bagged one Munro, Ben Lomond, but I won't be stopping there. Now imagine climbing that hill while rolling a massive boulder. Quite a silly and dangerous challenge. And once you're at the top, the boulder could do one of two things. It can either roll back the way you brought it up, or it will roll down the other side of the mountain in the way you were heading. Surprisingly, chemical reaction will behave in a similar way, and we call that mountaintop activation energy. And just like me on Ben Lomond, reactions can take easier pathway to get to the other side. So put on your walking boots and let's scale the heights of higher chemistry. This is Thing 4. What happens when chemicals react? Two possible reaction profiles. To help us understand, we can follow the energy pathways for a reaction thanks to a potential energy diagram and calculate the difference between reactants and products known as enthalpy change, delta H. An exothermic reaction will release some of the reactant's energy to the surrounding. The potential energy of the reactants will be higher than the products. The lost energy is released in the form of heat. The enthalpy change will be negative and the solution's temperature increases. An endothermic reaction will absorb energy from the surrounding and will lead to an increase in the potential energy of the products. The gained energy is taken from the surrounding also as form of heat. Delta H will be positive and the temperature of the solution will decrease. But for chemicals to react, they need to hit each other with enough energy. This is called activation energy. It is represented with a bell-shaped curve that represents the energy barrier that the reactant must overcome. The higher the activation energy, the harder it will be for the reactant to cross it, and the lower the rate of reaction. We call it activation because it is the energy required to break bonds and to get reactant closer. Activation energy can be measured from the graph as the difference between the top of the curve and the potential energy of the reactants. The reactant will then form an activated complex, which can be located at the peak. These are highly energetic, highly unstable compounds and could easily lose their energy either way, back to reform the reactant or forward to make the products. We can modify the height of that activation energy hill by using a catalyst. It will offer a different pathway that will be less demanding on energy and increase the reaction rate. It won't change the reactants or the product, but will give a much smaller activation energy. For example, common catalysts will adsorb the reactant on their surface, weaken the bonds within the molecule, and allow the molecules to collide with the right geometry. Once reacted, the products will then be desorbed, and the process can start again. And here you have it. You have activated your reactants and rolled that boulder all the way to the top. The activated complex can now reform the reactant, that boulder can roll back the way you came from, or the activated complex can pass the energy barrier and form the products. Your boulder can start rolling on the other side of the hill. Please do as many chemical reactions as you want to pass your higher chemistry, but I would not advise to carry a boulder up Ben Nevis. This was Thing 4. Thanks for watching.